3 minutes, done and dusted. Done. Okay, so let's have a look at plate tectonics. Now this is the science. Harry Hess did seafloor spreading, Alfred Wegener did continental drift, but plate tectonics is the science that explains and pulls together all of those things. Okay, and so we'll go from there, and we'll cover a few things. Recognise plates on the world map. There's a few large ones, about a dozen big ones, and some small ones. How do we can model seafloor spreading, we've done that already. Relate the occurrence of earthquakes and volcanoes to boundaries where plates line up. Consider the role of heat energy and convection currents in how plates move. And there's a whole bunch of new terms. So this starts to happen in Year 9 and Year 10 science, where you get these new terms coming through. And there won't be words, like for example, it gets a little tricky there, where you get lithosphere and asthenosphere, okay? But the rest of the things, I think you'll probably be okay, you'll be pretty happy with those. Okay, so what is a tectonic plate? Pieces of the Earth's, listen up, pieces of the Earth's lithosphere, which is crust and mantle together, that are approximately 100 kilometres thick. There's differences though, okay, between an ocean plate and a land plate. Okay. Now continental drift, you already know that, you got that from the other slideshow, the gradual movement of continents across the Earth's surface through time, and it's about 1 to 5 centimetres a year. That's how fast your fingernails grow. Okay, so that's the speed with which continents move. It's not very fast, but they are very big. There's a lot of force there. So if they get caught on each other, or when they run into each other, you get things happening. So if a continent is moving at 5 centimetres per year, how far will it move in 200,000 years? I will leave you to do that working. I'll give you a generous 60 seconds. Go! Like the wind. Oh no, I'll check your answer, but don't yell it out. Okay, Jess, but you have to show working. 5 centimetres, 200,000 years. That's 200 million. You're not supposed to show me. Yeah, Henry. Huh? Oh, sorry, 200 million years. Yep, you're right.
It's okay.
Oh, I should get you to do that in kilometres, shouldn't I? Yes, do a unit conversion. Answer in kilometres.
I did.
Okay, because it becomes more meaningful, and it's also a bit trickier.
I don't know. Oh, so it's just 5. Oh, okay.
Yes, that's pretty significant, isn't it?
Yeah.
Henry.
What are we doing?
Yeah.
Can I use a calculator?
A booklet down. Oh, you shouldn't need to, but you can if you want. Yep. Oh, no. So, no, kilometres, I said. Which booklet? Ruben, are you right? The new one. I think you're out by 1.
What?
I think you've got, hang on. That's right. Okay, I think. No, it's definitely not. It's definitely. Oh, that's centimetres or kilometres?
10 million.
No, it's definitely not that. Yes. It can't be 1,000,000 kilometres. That would go around. That would loop around the Earth. How many times? 200 times. I mean, I could. What if you've got a range?
What? Because it says 1 to 5.
Yeah, but I gave you a particular unit.
Oh,
5. So it'd be that one. Yeah, Ruben, I think you're right. Okay. So, how would you do the math on this? You would go, well, it does, you've got 200 million years, and it's 5 centimetres. Actually, you're right, I'm wrong. I should have said 5 centimetres a year. Oh, I did, sorry, I'm right, you're wrong. 5 centimetres a year. So it's 200 million times 5 centimetres, okay,
1 billion.
which is quite large, which would be 1 billion
centimetres.
1 billion centimetres. Now, how many centimetres in a kilometre? There's 100 centimetres in a metre. There's 1,000 metres in a kilometre. So it's 100,000. 1, 2, 3, 4, 5. I'm dividing that. So the answer I get should be 10,000 kilometres.
Got it.
So at that speed, in that amount of time, it could move as much as 10,000 kilometres, which is pretty extraordinary. Hopefully you got that right. Does everyone know how many centimetres are in a metre, how many metres are in a kilometre?
Yeah.
That's considered prior knowledge. Usually it's this stage someone burps at me and says, well, we're doing maths and science. Because it's numbers. Okay. Now, here we go. The Earth consists of 4 main layers, and there's a couple of special areas as well, but you should be able to draw that type of diagram. You should be able to draw from memory and label it. You don't need to know the kilometres so much, the kilometres not so much, but definitely you should be able to draw it. Now, the crust is a bit special. It's 8 to 64 kilometres. Okay, where do you think it's thinnest, the crust?
Ocean.
In the ocean, right near those rifts.
Right on the edge of
Right on the rifts. No, right on the edge of the rifts where the new rock is being formed. The crust is really only metres thick, but the average is 8 kilometres in the oceans, 64 kilometres on land. Okay, so the land's not very thick. The world's deepest drilled hole is what, 12 kilometres. I think we covered that yesterday. The oceanic crust is 8 kilometres thick. Found under the ocean floor. Dense rocks form there like basalt. Continental crust is up to 100 kilometres thick, found under land masses. And it's less dense. Highlight less dense. That's really important. Less dense means it will float. Okay, both of these will float in their own way, but the less dense one has really important implications when things run into each other. Okay, you'll see why. Okay. Now, can I change?
No.
Okay, so make sure you highlight those red areas. Remember, if it's red, it's important. And highlight that less dense. Yes.
Is New Zealand like normal man-made structures? Sometimes bombs and stuff can push entire countries a few centimeters closer.
They can cause. Look, you can do things and you can cause earthquakes.
Yeah.
And they're certainly detectable. They form ripples. But they're not going to move a continent. But I know that just fracking in the United States, where they're pumping water underground and other substances to try and get oil and natural gas out, is causing greater numbers of earthquakes. Yes? No, I don't have time to check it. Okay, bring it back after this class.
Yep.
Okay. Now, second one, mantle. Okay, down here, quite thick, 2,800 kilometres thick. Extreme heat and pressure make it a bit sludgy. It's liquidish, but it's just like pitch. Remember the pitch drop experiment we just watched? Pitch is liquid, but it's really not liquid like you and I understand it. And the mantle is even less so. It's, you know, as far as you and I are concerned, it's solid. It's rock solid. It's as hard as rock, but it does flow. Just really, really slowly. Yes? The lower you go down, the hotter it gets. Okay? It's about 20 degrees per kilometre. Okay? At this level in the crust. But the core is about 6,000 degrees. Okay? So, it's sludgy, slow-moving liquid. Patches heated by radioactive decay of uranium, thorium, potassium. So there's different areas of different temperatures, and that allows you to get convection currents going. So it's in the mantle. It's in the mantle. Draw this on your book that you're getting this business going on. Convection currents going on. That's the area that is interesting for plate tectonics. Okay? We've seen the pitch drop experiment. There's a wiki on the pitch drop experiment if you wanted to read about it. It has been running for a long time. When they invented air conditioning, it slowed it down. Remember, this is in Queensland. So, of course, in summer days it would be very hot, so the liquid would run faster. But now, of course, climate-controlled conditions, the pitch is fairly stable in the way it flows through. Now, next, there's a couple of, this picture here, on your, make sure you highlight this, because this picture is slightly different. Fine, we've got our crust, we have our mantle, but there's a couple of other areas between those two that are important for us. We're interested in the lithosphere, we're interested in the asthenosphere. These ones here, highlight those. These are the different ones. The lithosphere is that rigid layer of the crust, consisting of the crust and upper mantle. So it's what we run around on, is what we consider to be the lithosphere. But the asthenosphere is right up the top of the mantle. It's only a couple of 100 kilometres thick, and it is a bit plastic. So it's a bit liquidy. And that is what our lithosphere moves across. So the lithosphere is what plate tectonic plates are made from. So you can make a note there if you like. That the tectonic plates consist of lithosphere, okay? And they slide across asthenosphere, okay? Like an ice skater going across ice, okay? Because the pressure of the ice skates actually liquefies the water on top, and so you get a layer of slippery liquid on top of the ice, and that's what the ice skater is moving on. So that is a more accurate description of what's happening. Yes?
Is it actual plastic or just...
No, plastic means something that has some flexibility and some, in this case, like we say, teenage brains are plastic. But we don't mean literally plastic, we mean they are flexible, they're adaptable, they can do these different things, yeah. So we mean it in a descriptive way, not in a literal way, okay. So yeah, so stick on this. If plastic is a problem, stick with semi-solid, yeah. So it's even, the mantle itself is not solid, but it's pretty close to it. But the asthenosphere is more liquid again, okay. And that is what the lithosphere, which is the crust and upper mantle, is moving across. So that's what plates are made out of, lithosphere, and the asthenosphere is what they move on top of. And it's in the mantle, it's the convection currents that are moving them. Now, why do we get convection currents? Not a literal question. It's because of what's happening in the outer core and the inner core. So, slightly different picture here. The outer core is, see the temperatures are quite high, okay, and it's liquid nickel and iron. That's a lot of, that's 2,200 kilometres deep. So that is one heck of a lot of nickel and iron, okay, and it is a thick liquid, and convection of liquid metals in the outer core creates the Earth's magnetic field. So again, in this liquid we have convection currents running. Okay, and that is what creates the Earth's magnetic field. In this, now you're not tested on magnetic field and magnetosphere. Note the magnetosphere is blue. We don't test you on that, but the magnetosphere is something you should be aware of because it's keeping us alive. So the sun every so often will burp out enormous amounts of charged particles, and if you were exposed to those, you would die. But what happens with those charged particles? Hit the magnetic sphere. The charged particles have an electric charge and therefore a magnetic charge, and when they hit the magnetic field of the magnetosphere, they go around the planet, and you get these beautiful northern lights and the southern lights. And so if you're visiting the Antarctic or maybe Alaska, you'll see the northern lights, these beautiful, and that's from charged particles from the sun being directed around the Earth because of our magnetic field. Yes?
Is that the same stuff as like the ionizing radiation that comes off the sun?
No, they're more photonic, so they're not actual particles.
Oh yeah.
So they act like a wave, but in this case these are charged particles, and so they are just being directed around the atmosphere. See, the atmosphere blocks gamma. The atmosphere blocks gamma, it blocks X-rays. The ozone layer blocks UV. So that's what stops those forms of radiation. but this is something else entirely. If we had an atmosphere but no magnetic field, we'd also be in trouble. The atmosphere would block UV, X-ray, gamma, but these charged particles would get through. And so this is actually really important for us. The inner core is the centre of the onion, if you like. It's about, the radius, it's about, as a ball, 2,600 kilometres in diameter. It's a solid iron ball, iron nickel alloy, and it's about the same temperature as the surface of the sun, about 5,000 degrees, 6,000 degrees, give or take. This is the difference. This is solid, this is liquid. Highlight those differences. Because this is liquid, and because there are convection currents, you get an electromagnetic field. And that is what is keeping us safe. Have you seen the magic physics machine that they have here? You turn the handle and you make electricity. You should know this from year 8. How do you make electricity? What turning things have to happen to make electricity? Because all the power plants you looked at turn things to make electricity. No, they just transmit. Generators are a bit general. Coils of it's copper wire, and they're near a. What are they near?
Is it magnetic fields?
Yeah, they're near a magnet. If you take a magnet and you put coils of copper around it and turn them, you make electricity.
Yeah.
Now I can do that on this desk using a little thing they have next door, and it makes electricity. The light bulb glows, and that's what every power plant you've ever thought of, from nuclear, which seems very high tech, and it's 10 years to build a plant that costs $10 billion. But all it's doing is heating water to turn a turbine, to turn something, coils of copper near magnets, and make electricity. Or you could have a steam, some kind of steam device. They're all steam devices. But you could have a primitive one, burning coal. Okay, burn coal, boil water, turn a turbine, make a turn, and you generate electricity again. Okay, so when you turn copper near a magnet, you get this, you get electricity, and so there's this electromagnetism. Again, you don't study that at this level. Yes?
If the centre of the Earth was so hot, then why is it all solid?
Pressure.
Okay.
And if you press anything hard enough together, it's effectively acts like a solid. Yeah. That's actually a really good question. But there are no currents in that core. It just acts like a solid. But there are currents in the other one. Now, tectonic plates, section of the Earth's crust that move on the Earth's surface, they consist of lithospheric mantle and crust material. So basically they're lithosphere. Okay? That's what a tectonic plate is. And I mentioned that before. The lithosphere consists of a dozen major plates and dozens of minor plates. And you can start to see these. Look. Where's a nice easy one? So this is not a map of the Earth, this is a map of tectonic plates. There's the Australasian plate, and Australia is sitting on that. Where the heck is Australia? Oh yeah, we're so far down.
We're on the other
There's-
side.
We're on the top.
Or on the left?
Other side.
What? Where?
Left side.
Oh, yeah.
That's the top of Australia, isn't it?
That's
That's on
Ah, sorry. Don't listen to anything I said there. Okay, there's the Australian plate. That's the Australian plate as well. Sorry, this one here. Oh, there's a little pointer. Sorry, the brown one is the Australian plate. There's Australia there. Now, is Australia near the edge of a plate?
no
earthquakes. I'll give you that one for free. Australia's not near the edge of a plate, no earthquakes. If you are near the edge of a plate, earthquakes. Because that's where stuff happens. Things are running into each other. That's what these arrows mean. Look, these guys are sliding past each other. These guys are pressing into each other. In a couple of cases, they're pulling apart from each other. Okay? So all these things are happening. If you look up here, we're looking, this is the Filipino plate. This is these areas of Asia where you get a lot of tectonic activity, including Japan, where Japan straddles 4 plates effectively. So heaps of volcanic activity, heaps of earthquakes, and so on and so forth. And so this is this key idea. Earthquakes and volcanoes occur at boundaries. Is Australia near a boundary?
No.
No volcanoes, which is bad, but no earthquakes. Volcanoes are really important for making rich soil. they bring up all of these minerals. Okay, that's why Hawaii looks like a paradise. It's near the equator, heaps of sunlight, heaps of rain, heaps of minerals in the soil. Everything grows like crazy. But look at Australia, our soil is shot because we don't have active volcanoes. So every year our rivers, like on all continents, take minerals to the ocean. It's really important that they do so. So we just erode and erode and erode this continent. It's easy to, mining is easy because we're very flat, we don't have mountains. But we don't have rich soils. Yes?
But it shows on the map that Hawaii is in the middle of its ocean.
That's right, but Hawaii is special. It's on a hotspot. So Hawaii is a special one. There's a special, we'll talk about volcanoes and hotspot volcanoes. Sometimes you get, it's like a laser just coming through. And it stays there for millions of years. And it just forms a volcano, and then the plate moves away, and the volcano dies, but it forms another volcano. It moves away, moves away, moves away. And you get a chain of volcanoes that become islands. Okay, now, here we go, seafloor spreading. Great. You know about seafloor spreading already. Harry Hess suggested the rocky crust has been formed. Now you need to get your head around that diagram and spreading outwards. So young rocks near the trenches. We've covered seafloor spreading. Subduction is what you saw on the style exercise that I gave you. Less dense or fast ocean plates sink beneath another plate during collision. It slides into the mantle, causing melting. Let's look at this diagram. We have this ocean plate is moving to my left. This ocean plate is moving to the right. And when they run into each other, they start to slide under each other. It's actually the faster moving one will slide under the slower moving one more so. But see that big crease there? That forms a huge trench, and you get volcanoes associated with this activity, and we'll explain that. Okay? There's a mid-ocean ridge. The rocks are moving away from it because of a big convection current pushing away. Here is land meeting ocean. This is the ocean here. This is land. And again, the ocean one is sliding underneath. You get a big trench near the coast, very deep. And again, you get volcanic activity. This is a volcanic activity island arc, and this is just called a volcano arc on land. Okay, so it'll go all the way. You get volcano all the way up the coast, volcano all the way up the coast. Okay, and you'll also get some fold mountains probably as well. So it'll ripple. This one will ripple and buckle, and you'll get some fold mountains that aren't volcanic. So those ones there are probably, may as well fill that in, fold mountains. And you'll also get some volcanoes. So you get this combination of two things going on. Now, let's see. Subduction occurs when a dense ocean plate slides under a less dense continental plate. So that's what's happening here. This one is sliding under, and as it gets pushed under, it melts down. And there's a lot of water associated with that. So there's heat, there's water. This fragment gets all frothy, and it starts to bubble through any crack it can find, and you get a volcano forming. In this case here, the faster ocean plate slides under the slower ocean plate. So this one here, if it's faster, goes underneath, but it's not an exact science. There's going to be a bit of grabbing and tearing and whatnot. But again, trench, trench. In this case, in both cases, you have ocean trenches. It can be very deep. This one, the Marianas Trench, is off Indonesia. It's one of these. It's about 11 kilometres deep. My son would say it's 10,994 metres deep, he'll tell you. So it's not quite 11 kilometres. But it is very, very deep. Okay? And so that's what's happening there. Let's see. A deep trench forms, as do volcanoes, island arcs, or on land, volcanic arcs. So you can get a volcanic arc here, or you can get fold mountains here. You can get an island arc here. They call it an island arc because those volcanoes eventually die out, and then you've got islands. So that's how you make new land. And last year alone, I think there were 3 new islands made out in the ocean. So if you got there first, could you claim them?
No.
Probably not. If they're close to anyone, they're just going to claim them themselves.
Have to buy them.
So, but yes, they wouldn't be very pleasant at this stage. Can I change that slide?
Yeah.
Yeah. So that's quite a bit of information, but you do need to know that information. I modified this slideshow heavily this morning before I came to class. Okay, here's ocean versus continental. The more dense, oh, that's not quite correct. Oh, that is, the more dense ocean plate subducts under the less dense continental plate. If you have water and subduction, you get volcanoes and a volcanic arc, and you can get fold mountains. Okay, so here's a volcanic arc, and when those volcanoes die, you get mountains, but you're also going to get some rippling because stuff is running into each other. So you get some fold mountains. Now, if you get ocean versus ocean, the faster ocean plate subducts under the less dense. Oh, that should be slower. Let's fix that up. That's the beautiful thing about electronic slideshows. Oh, look at that. That's a typo. Big typo. Slower ocean plate, that should be. There you go. So the faster ocean plate subducts under the slower ocean plate. Water and subduction, you get volcanoes and you get an island arc. Okay? And then continental versus continental, guess what? They're the same density, and when they run into each other, what do you think happens?
Earthquake.
Well, they just build up.
Mountain.
You get the Himalayas or something like that. Okay? And so, because both plates are buoyant, not dense, and the kilometres wide rock slivers are pushed up and bunch on top of each other, forming huge fold mountains like the Himalayas. So Everest is still getting taller.
But what are the Himalayas?
Sorry, what are the Himalayas?
Yeah.
The mountain range. You know the mountain range in Asia? World's highest mountain, Mount Everest?
Oh, I know that.
Yeah. Mount Everest is part of the Himalayas. It's a huge mountain range. They have really high mountains right down that range. Everest just happens to be the highest. Yeah?
Oh.
So Everest is about, what is Everest?
12. It's got to be 12 again.
No. It's around 10 kilometres, I think.
Oh,
I thought it was more.
Or, no, you're right. It's 8,000. It's something like 8,898 or something like that.
From sea.
Okay. So from sea, yes. So what we have here is three different things happening. We have ocean versus continental, ocean versus ocean, and continental versus continental. And because of the different densities and the different speeds, you can have slightly different outcomes. If water, what do you notice here? Circle that. Water and water. What do you get if you have water and subduction?
More water.
You're getting a volcano.
A volcano.
Every time.
A
See, look at this
volcano
one
is
here.
water.
Ocean plate, land plate. They run into each other. There's water associated with that. That makes this all frothy. Volcano. Ocean, water associated with that makes everything frothy. Volcano. Okay? Land, you don't get a volcano. There's no water associated with that in a meaningful sense. So you need the water associated with it to make the magma frothy and a bit bubbly and some pressure because of steam, and that will drive that up through any cracks, and then you'll get a volcano forming. Okay? And so that's really important. So there's an island arc there, or a volcanic arc, because that's died. That volcano has died. And here we have a volcanic arc, or you can have fold mountains as well. That can form. But this one here effectively just forms fold mountains because they just run into each other. Okay? Any questions? So they build up and they build up. They go down as well. They both go down, they both go up, but it's mainly that thing. Okay. Now, this particular slideshow is important. It's probably, and the test that you do when you come back is probably half of the questions on it will be covered just by this slideshow. So most of the slides on here are critical. Okay, convection current, we talked about that. Any rock over a hot patch in the mantle will rise and cooler rock will drop, okay? Or rather, so what's happening here is because of this hot core, you've got this convection current forming in the mantle, and moving ultimately the continental plates either side. The lithosphere tectonic plates float on these convection currents like pieces of toast floating on very hot, dense soup. So that's what we're doing. Both the ocean crust and the ocean dense crust and the land, or the ocean dense lithosphere and the continental less dense lithosphere are all floating on mantle, which is very, very dense, and yeah, just sort of slowly but surely moving around. Okay. Can I change that one? There's not much to write on your slide if I remember correctly. Okay. There's another example of that. There's something we haven't talked about before, a hotspot, and we'll talk about those as well. But the main idea of this is convection currents moving things around. There's a mid-ocean ridge, okay, and India and the Red Sea here, but this particular continent here, the African continent, are moving away from each other, away from that mid-ocean ridge. So slowly but surely, that ocean is getting bigger. And another ocean somewhere is getting smaller. Now, hang on, I just want to check something quickly. Okay. I want to do two more. Okay. A converging, or these are the types of boundaries that we deal with. Now, I'll explain this, but we might have to finish it next class because I have 4 minutes left and I do want to finish the video. So stop writing for now. Let's just talk about this and we'll come back to this next class. So I'll just explain it. At a converging boundary, two plates come together. They could be ocean-ocean, ocean-land, or land-land. Also known as destructive boundaries. Rock is melted at this location, so the mantle is recycled. So this beautiful old rock here, it contains heaps of fantastic fossils, and it just gets melted away. And you get fold mountains forming. With a diverging boundary, they separate from each other. Constructive boundaries. New rock is being made on the ocean floor. Okay, and so it does happen that lands are impacted by this as well. No, don't pack up, don't make noise, just keep an eye on this. And a transform or a scraping boundary is they're going beside each other. Okay, and this is what's happening in California, and they're building up pressure. They can get stuck and build up pressure and then slip and you get an earthquake. These are conservative boundaries. They conserve rock. They neither make new rock or destroy rock. They can make fold mountains as well. So anything where rock is pressing against rock will tend to make mountains. Fold mountains, mountains formed by crust crumpling upwards as plates collide. Okay. As I said, I just want to show you one last thing to finish the slideshow. This idea of the ring of fire. Okay. The ring of fire is the most volcanic area on the Earth, and it's because of converging plate boundaries. Okay. You've got water, you've got boundaries coming together, so of course you get volcanoes. So you get volcano, all the way around here. And you get trenches as well. That's what these blue things are. Trenches in the ocean. Challenger Deep is the deepest point on the Earth. That's the one that's 6 metres short of 11 kilometres. Okay? So this is an area of extreme volcanic activity. This is, now where's Australia? Great. So when you see a world map and someone asks you to find the ring of fire, just above Australia, around to the right, okay, through to South America, okay. This area here is very important because on a map, find a volcano, South America. Find a fold mountain, South America. Find a trench, South America. Remember South America. South America is your friend. Here's another one. Here's a heat map. Here's a heat map of the ring of fire. Out and around, very hot volcanic activity. So this is where most volcanoes are found. But there are volcanoes all through here as well, okay, because of converging boundaries. And lastly, this particular map, stop, I didn't say pack up, I just said pay attention. This particular map, critical for your exams and tests because it shows fold mountains and it shows earthquake zones, and you already know South America is volcanoes. So there's fold mountains, earthquakes, Because on the last 3 exams, they said, draw a circle around a volcano, draw a triangle around an earthquake, draw a square around a fold mountain, boom, boom, boom. Done, dusted. That will work for anything around the ring of fire effectively, but that particular area there is very rich. Guys, well done. Go to your next recess. And I'll